Hello, my name is Matt Max. Welcome back to the second part of microphone lingo, where I explain all the basic terms that you hear when you go shopping for microphones. This time I want to talk about noise, linearity, and phantom power. So let's get started. When talking about noise, we have to differentiate between different kinds of noise. There is environmental noise like this. This is environmental noise, right? This is a lot of environmental noise. Stuff happening in your scene that you do not want to pick up, but you do pick up because it's happening. Let's say you want to interview somebody at an airport, right? And it's just really loud on this airport terminal. That's a lot of environmental noise. Other sources of environmental noise, wind, right, and echo. Those are the main three sources of environmental noise. So what can you do against it? Well, against wind, there are special wind guards that you can buy, that you can put on top of your microphones. You probably saw your weatherman, right? He has a microphone with this huge fur thingy on top of it, right? That's to combat the wind sound, right? So there are lots of things you can do against wind. For environmental noise, depending what noise it is, you can use a very directional mic, like a shotgun mic, that doesn't pick up, for example, the crowd next to you. If you actually find, here it is. You can use a microphone like this, a shotgun mic that won't pick up sounds that comes from the side. The problem is, let's say I point the shotgun mic at you, okay? And behind you is a street. And we normally don't hear the street. But since the shotgun mic is so directional, it will pick up the street, right? It will pick up sound from really far away, even if the sound is pretty quiet for our ears. So if there is a street behind you and I point the shotgun mic at you, I might not pick up the crowd from next street, but I will pick up the street. So you have to think about, how do I want to use my shotgun mic, my very directional mic, to not pick up noise? And usually what you do is you use a boom and you have the shotgun mic above you pointing downwards. This way you have the least noise. So that's one thing you can do. Other noise includes this, right? That sounds like crap. And for this you use a pop filter. If I do this now, I really have to use my whole lung capacity for you to even hear it. That's so well this pop filter works, right? So that's what you can do against environmental noise. But there's another form of noise, and this is electronic noise. Whenever you have an electronic device, like a microphone, like an amp, like speakers, like your camera, like your CPU, you always have noise. You have random electrons just moving randomly around. And against this, you cannot really do a lot, right? You have to get a microphone that has a low noise, yes, a low noise. And the other thing you can do is to just have a good, clear, loud signal. If I record something that is very quiet, then I have to amplify the signal a lot. And when I amplify the signal, I also amplify the noise. So what you need to do in order to not get a lot of electronic noise, you need to get a good signal to noise ratio. Your signal has to be way stronger than your noise. That means that your signal has to be pretty loud. The louder, the better, usually. Okay? So again, our example with the shotgun mic and the interview, I want to get the shotgun mic as close to this guy that I'm interviewing as possible to get the lowest amount of noise. It means I want to get my boom mic, right, as low as possible, but just outside the shot, like this, okay? In some shots, you actually cannot use a boom mic anymore because the distance would be too high, and if your shot is a long shot, if it's really wide angle and so on, you cannot use a boom mic because it would be too far away, and the signal to noise ratio wouldn't be good. In this case, you use a lavalier mic, and I speak about this in the next episode. But yeah, that's basically the only thing you can do against electronic noise. Get a microphone that has low noise and get a good signal to noise ratio by actually getting the microphone close, right? If I would take this microphone and put it on the wall right there, my voice would be way more quiet, the signal to noise ratio would be way worse, and you would hear a lot more noise. Linearity describes how close the signal that your microphone picks up, so in my case my voice, is to the signal that comes out of the microphone. Alright, so in other words, it describes how much the microphone distorts your voice or whatever you want to record. That is called linearity. There are two numbers which measure linearity. Number one is THD, or total harmonic distortion. That's a percent number. The lower the better. Usually you get something along the lines of 1%, and you shouldn't pick up a mic that has more than that. 1% is pretty much standard right now. And the other number is frequency response, which basically tells you which frequencies your microphone can pick up without distorting them too much. Human hearing range is 20 to 20,000 hertz, so it should be along those lines. It gets, however, more difficult, like always. If you pick up a dynamic microphone, like a live singing microphone, it doesn't distort all sounds the same. It distorts different frequencies, different sounds differently. Right? And if it's a good microphone, it will actually come with a datasheet. And in the datasheet, you will find a graph very close to this one. Now this graph is actually quite simple, so let me explain what you see here. This is the amplification in decibel, and this is frequency. This is a logarithmic scale, right? So it's not like 10, 10, 20, 30, it's like 10, 100, thousands, okay? Here's 100, here's 1,000, here's 10,000. The black line that you see here is a dynamic microphone. Dynamic microphones, I will talk about this again in the next episode, work with a magnet and a coil, and the problem is that dynamic microphones, because they are working with a magnet and a coil, cannot pick up all frequencies the same. And you see it in this line. You see that around maybe 200 hertz it starts to record pretty good, right? And here you see it's pretty flat, and then suddenly at like 3000 hertz it suddenly goes all over the place, right? That means that this microphone, this black one, and this graph is from a Shure SM58, which is pretty much your standard singing microphone. It means that this microphone is not very linear. Okay, you see that this graph goes up and down a lot, so it's not very linear. The flatter this graph is, the better the linearity. As a comparison, I have this red line. This red line is this microphone. It's a Shure SM01. And you see that the Shure SM01 does not go all over the place. It goes up and down a little bit, yeah, sure. But it's pretty much one straight line. That means it's really, really linear. That means it picks up all those frequencies almost the same, okay? It doesn't matter if I record 100 hertz or 15,000 hertz. The microphone will amplify and pick up both signals the same, right? Whereas a Shure SM58 will pick up 100 hertz and 7,000 hertz completely differently, right? So the red line, flat graph, good linearity. The black line, not a very flat graph, bad linearity. But bad linearity is not necessarily, well, bad, okay? For some people, a dynamic microphone actually sounds better than a condenser microphone like this one. Because it's not linear, different parts of the voice get amplified differently. So you can sound more interesting. And actually, manufacturers of dynamic microphones say, our microphone boosts special frequencies so your voice sounds more dynamic. That's bullshit, okay? It's true that it boosts different microphones, but not because they want it to, but because they have to, because it's a dynamic microphone, right? So you can sound better with a dynamic microphone, but you can do all of this in post anyway. You can record yourself with a condenser microphone, which is very linear, and then you can just add all this in post-production anyway. So I don't see the point. But yeah, bad linearity is not necessarily bad. And another thing you have to look out for is that you need a good linearity in the frequency range you actually want to record. If you want to record a bass drum, okay, both of those microphones won't work. Because a bass drum is about here, right? And they both aren't very linear in this area. So it really depends on what you want to record. If you want to record human voice, a typical male voice is between 85 and 180 hertz. That's the fundamental frequency. And a female will be between 165 and 255 hertz. But that's a fundamental frequency, okay? Your voice is not only your fundamental frequency, it's all the harmonics of the fundamental frequency, which are basically integral multiplies. So if your fundamental frequency is 100 hertz, you also have 200, 300, 400, 500 hertz. If your fundamental frequency is 80 hertz, you also have 160, 2 times 80, 240, 3 times 80, 320, 4 times 80, and so on hertz. And in the end, you get a frequency range for human speech, which is about 60 to 7,000 hertz. That is the green area. This green area, that is human speech. Okay, if you want to record human speech, you want a good linearity in this area. And you see that the condenser mic, the red line, has a really good linearity in this green range, whereas the dynamic mic doesn't. A lot of big microphones like this one actually need an external power supply to work. And this power is supplied through the same line that actually the sound goes through the same cable. And this is then called phantom power. So you need a device that's actually able to support your microphone with phantom power. Otherwise it won't work. It's as simple as that. There are some microphones where you can put a battery in it, and that will provide the microphone with power. In this case, make sure that if you put phantom power in it, remove the battery first, because otherwise the battery might actually break, and you don't want that to happen. My name is Max. Thanks for watching this episode, and tune in next time.